So this unit is about log functions. So for the middle unit assignment, the question 1, they ask to determine the domain range for the function under a vertical reflection. We know if the A, which is if A negative, the function can have vertical reflection. And let's see. So if we use log 2, because base is greater than 1, so we do have increasing function. I choose 3 points. And if we only reflect, so the x-coordinate won't change, but all the y values will be opposite. So after reflect by the x-axis, so you can see here, the domain is still x strictly positive. The range still doesn't change. So therefore, for vertical reflection, won't change both the domain and the range. So for question 2, the question asks, if there's under horizontal translation and vertical translation, how they gonna change or whether will be changed the domain and range. So by the generalized transformation form, we consider the A is still 1, K is still 1, but there are horizontal translation and vertical translation. By the general rules, if the P here is positive, the graph actually will be horizontally translate P units to the right. If P negative, the graph gonna horizontally translate P units to the left. So if Q value positive, the whole graph gonna shifting Q units up, and similarly, if Q negative, the whole graph gonna vertically translate Q units down. So the domain, you can see here. So the vertical asymptote gonna change to the P value, and here because I assume P x minus 2, so P equal 2. The whole graph gonna horizontal translate 2 units to the right, and shift 1 units up. So in this case, the domain will becomes 2x strictly greater than P, and range there's no change on the range. Still y belongs to all real numbers. The vertical asymptote for this particular example goes to x equal 2. So question 3, for this function, we can see the base function we do have log base of 10 for x. And first, I choose 4 points from base function. Here are the coordinates of each point. And I also write the mapping rule. We know in general we have x over k plus p, comma, ay plus q. For this particular example, we do have a equal half, k equal 1, p equal 0, and q equal negative 4. So that'll be vertically compressed by half and vertically translated 4 units down. Then for the 4 points on the base function will be translated to these corresponding points. So for part B, I plug the transform function with the calculated points. So the black one here, which we do have f of x. And part B, the part B asks to draw y equal x and reflect to get the inverse. So we do know graphically to find the inverse function, we just need to switch xy point. So we're gonna have xy coordinate for the inverse function. So I plug them. That's given by this blue line. And for part C, for the domain, you can see here, the domain for the inverse function, which is blue, we do have x belongs to a real number, but the range, however, will be strictly positive because the inverse function here is an exponential function. So here we do have, instead of vertical asymptote, which is from the from original function, the inverse, the blue line, actually it has a vertical asymptote, which is y equals 0. So part D, they ask to algebraically to find the inverse function. So first, I recap or rewrite the given log function. For the inverse, I switch xy, then rearrange to get the log of y on the right side and everything else on the left side. We do know in order to get y, log function and exponential function are inverse of each other with the same base. We know by default log the base of 10. So we just took 10 power of each side to convert as an exponential function. So by cancellation rule, if 10 base part of log y, this base and log 10 cancel out, we have y left. So here we do have the inverse function. And clearly, this tells us this is an exponential function. And the domain of the inverse function will be the range of original function.